We're good?
Yeah.
Okay. All right, welcome everybody. Let's finish up the full proof of the composition lemma from which the main result follows. So, lemma. So the lemma states that let n be an integer be greater than 2. And then, well, let's say greater than 3 to be safe. So let n be an integer greater than 3. We're going to assume that a function f in Zn to the Zn has a unique attractive fixed point, so we're looking at a functional tree. Okay, we assume this. This is 1. So if this is true, then this is the final punchline. Then the claim is that the maximum over sigma in Sn of the cardinality of edge labels of GF2 this maximum is always less or equal. We want less or equal to the maximum over sigma, basically the same expression, the cardinality of edge labels sigma f, sigma inverse of I minus I. Okay. I in Zn. Okay. So this is what we want to prove, that the maximum number of edge labels in GF2 is always smaller or equal to the maximum number of edge labels in GF. Okay, all right. So let's make a few observations that we can elaborate on. So the first easy to see observation is that without loss of generality, you can assume that, so without loss of generality, it suffices to show that GF to graceful implies GF graceful. The point is that if there was a functional tree for which the maximum is not attained, it would violate this lemma. It would violate the inequality. So basically, this is what we want to show. If you show this, because every tree eventually reaches the star, which is graceful, this is what we want to focus on. Now, if you state that GF2 is graceful, that means that this maximum, you can assume that this maximum is equal. This maximum you can assume is equal to n. All right? Okay, so now we're ready for the proof. So that's what we can assume without loss of generality. Okay, so step 1 of the proof is to start focusing on our polynomial. So GF2 being graceful means that the polynomial product over I less I different from j of xi, let me write xj minus xi times x f of j minus j squared minus x f of I minus xi squared, that this polynomial is not congruent to 0 modulo our algebraic relations. X, I, let me write k, and k is 0. Okay, so this is what it means for GF2 to be graceful. So I want F2, so let me put here 2 and 2. Okay, so GF2 being graceful means that this polynomial, which tests, which certifies gracefulness, is not congruent to 0. Okay. Now, the only hard step in the argument is to make the edges of GF appear. In this expression, there's no edge for GF. I want to make the edge of GF appear, and I want to see what role they play. All right? Okay, so here's how we're going to make the edges of GF appear. So I'm going to rewrite this expression, the polynomial, like this. So this polynomial is product I different from j of xj minus xi. By the way, if there's any question, don't hesitate to ask. Okay? All right. And here is going to be x f2 of j minus xj minus, it's not a mistake, I did omit the square, f2 of I minus xi. And here I'm going to multiply by x f2 of j minus xj plus x f2 of I minus xi parentheses. So I basically did the a square minus b square is a minus b times a plus b. This is a difference of squares. So far, I haven't done anything out of the ordinary. And we still don't see the edges of GF. So now, I'm going to do the telescoping trick. So I think I can erase now the statements. So I'm going to do the telescoping. This is the telescoping step, which is now going to introduce the edges of GF. So we're now going to do the telescoping step. So let me do that. So here's the telescoping step. So again, I have product I different from j. Here I still have xj minus xi. Everybody follow so far? Okay, and now I'm going to have x f2 of j minus x f of j plus x f of j minus x j. So here I've introduced a 0, a very appropriate choice of 0. And the reason I chose this 0 is because you can see this is an edge difference occurring in GF. And this is also an edge difference occurring in GF. So initially I had edges which only occurred in GF2. And by introducing this xf minus xf plus xf, I've broken up the edges in GF into the edges in GF2 into 2 edges in GF. All right? Okay. I'm going to do that for the other guy. So the other guy is here. It's going to be x. So because of these expressions, we see why it's very helpful to have a large board. Okay, and here is plus in parentheses, like this. This asks for help. What should I write here? What should I write in this parenthesis? Any idea? Very good. xfi minus xi. Okay, good. All right. So this is the minus part. Okay. I need to do the same thing for plus. All right. So assuming we remember this, so let me write it. Let's take advantage of this massive board that we have at our disposal today. So let me do it. I'm going to multiply this expression here by x. Let me ask for help. This is f2. It looks very similar to this. So j minus xf j in parentheses plus here is going to be x fj minus xj. And then this guy, I now want to do plus. So here there's a mistake that we did not catch. This minus has to distribute, right? So it has to be minus minus, right? Unless, oh, they're in parentheses. Okay, so then I'm missing a parenthesis, right? So this guy was open. I'm closing this guy here, And these parentheses here. Okay, all right, so let me put this in parentheses as well, just to be safe. Okay, and here is x f2 of I minus x f of I. And then here inside is plus x f of I minus x I. Okay, so I close this, and I close this. This is the expression we're looking at. This is the expression we're looking at. So far, so good? Okay, so I wanted to make the edges of GF appear. And now what I want to do is I want to sort of group, this part and this part. And I want to group this part and this part. And to do that, I'm going to use a multibinomial identity. So the multibinomial identity that I'm going to use makes the following claim, that if you have a product, so here's our multibinomial identity. So it says, if you have a product like this, product over k, k is in your indexing set, doesn't matter. And here you have alpha k plus ak. And on this side you have a beta k plus bk. Okay. And here our ak is this guy. That's what we want. So this is alpha, this is the A, this is the beta, this is the B. Okay, anyway, so if you have this, the claim is that this expression is going to be the product over K in your indexing set of alpha K plus beta K. That's the part I want to pull out, definitely, for each factor. And here, the rest is a messy sum that you can write as sum over product of sk tk has to be 0. This is product over k. And sk comma tk has to be 0, 1. And then it's exactly what you would guess. So here is now product over k, and here is alpha k, 1 minus sk, this is ak, so ak, 1 minus ak, and here's alpha k, sk, okay, and here is going to be plus bk, 1 minus tk, and here is beta k. So we should stop and look at what happened here. So all I'm saying is that if you multiply these, in every single term you need to choose either you're taking alpha k plus beta k, or you're taking the rest. In every term you're making one choice. So there's only one way you can pick alpha k and bk, and this amounts to setting all the sk's and bk's to 1. If all sk's and bk's in this sum are set to 1, then you're going to pick alpha k plus beta k. And for all other combinations, you're picking some setting where sk is equal to 0. One of the sk or one of the tk has to be 0. So this is tk. Everybody sees? Okay. So if I use this identity here, and let me show you how I'm using it, I have to spell out what is my alpha k. So in this factor alone, I want to think about this guy as my alpha ij, and I want to think about this as my aij. Okay, this is this is the first factor, and here I want to think about this as my beta ij, and I want to think about this as my bij. All right? So in the first factor, I'm going to apply this multibinomial identity, and I will also apply the multibinomial identity in this second factor. So far, so good? Yes? All so I'm hesitant to write, to erase everything, but I think it would be helpful to split these products into two products so you can see what's happening. So I want to split these products into two products, make it clear what's happening with the multibinomial. Everything else doesn't. No, I think I agree. I agree. I mean, at this point, I don't think it has any effect on the proof, but yeah, so let's add this condition, sk equal tk. What's important to me is that I want to isolate this part of the sum. And so I have to double check this indexing sum, but I think definitely there should be 2 to the cardinality of I in the sum. Because either you take this alpha k plus beta k, or you don't. And for each one of the choices, for each one of the term, you're actually choosing either to take it or not take it. So there should be 2 to the cardinality of I choices. So I think I agree with that. Okay, so that said, I want to rewrite now the products in a way that we can see the two pieces at work. So the first piece, I'm going to write here product I different from j of xj minus xi. And here is the first product. Okay. So the first product, I'm going to rewrite it. So this is I different from j. And now, let's write cleanly the first product. So the first product looks something like this. So the part that I wanted to pull out, my alpha k, is xf2, is xf, is xfj minus xj. Okay, minus here x fi minus xi. Okay, so this part here is what I'm calling my alpha ij. All right, and then I have the other part, which is right here, and it looks like x f2 of j minus x f of j. And here I have minus x f2 of I minus xi. Okay, all right. I know the expressions are somewhat messy, but this is unavoidable. So this is the first factor. And then there's a second factor where instead of having minus, I'm going to have pluses. So let me write that second factor right here. So the second factor looks something like this. Product I different from j, I different from j, of here, I'm going to put square bracket, and here is, okay, so let me ask for help. Any idea what I should put here? Any idea? Anybody following? What should I put? So here is the minus. I need an expression similar for the pluses.
F of j.
Yeah, so this is f of j minus, here is x, f of I minus xi. Okay, so this guy is the first. And now I need to plus, so here's a plus now. A plus, and on this side is going to be x f2 of j minus x f of j plus x f2 of I minus xi. Okay, all right. Now I've written the two products. So remember what we had before was we had xf2 minus x. Yes, question?
Oh, sorry. Just in the first product, is
Yes.
it the whole square bracket? The first whole square bracket is aij, or just the first term in it is aij?
Very good. So in the expression, the whole first bracket is what I want to call alpha ij.
The whole second bracket is.
And the whole second bracket is what I want to call beta b. So this is a ij.
That's different.
Yeah, I think.
Yeah, it's different. Okay, yeah, but I think this is really what I want.
Okay, we can understand that. But
Because if you take this, then you are looking at basically the expression, the polynomial for PF. We started with a polynomial of F2. And the polynomial F2 is looking at the differences between the edges in GF2. Yes, I see. Okay, yeah, so this is very confusing because what I'm doing here and what I did in the paper is different. But I think this makes it simpler because there's only one term. There's only two terms to focus on. So if you do this, if I do what I'm writing on the board, this is what I'm looking at. I'm just looking at alpha ij plus aij. That's all. This makes it much easier to follow. Right? So I have alpha ij, I have aij. And then if you do that, then it's clear that the product, the first product is going to be product of I different from j of alpha ij, right?
That you need the SK and T case.
Yeah, absolutely. So here it's going to be, now it's going to be sum over, okay, so sum over sk. So I only need one s, right? It's sij. I only need one sij, right?
Yeah, but if you also consider the second part of the product, that is beta ij plus bi.
Yeah, so I'm going to do the two products separately. I'm not going to mix them. Yeah, I'm not going to mix the two products. Otherwise, we're going to be here forever. So I'm going to keep one product on one side and another product on the other side for the discussion. So there's only one term. Okay, so we can roll.
It's rolling.
Okay, so there will be some editing to do, but now at least it's clear. Okay, all right. So let's clarify this expansion because this multibinomial identity, as written, is not what I had below. So let me clarify this. So it's much easier to have two terms in the multibinomial identity. And if you have two terms, then the first guy, this product, what I want to isolate is the alpha ij's. So I want to isolate product of alpha ij's. So if you isolate product of alpha ij's, what you're left with is the sum over sij, 0, 1, and the product of your sij should be 0 over I different from j, right? So if you isolate this guy, the product should be 0, and here you have alpha ij to the sij times aij to the 1 minus sij. This is much easier to follow what's happening. Okay, so that's the first factor. The second factor, I'm going to do the same thing. I'm going to call this, I want to call this guy beta ij, right? And I want to call this guy bij. Okay. All right. Now, of course, if I do this, I'm going to have two terms. One that has, okay, so let's write this factor here. So this guy, I want you to think about this guy as product of I different from j of what? So this is going to be alpha, no, this is beta, actually, right? One should ask for help. Beta ij is plus, and now I can use help. So it's sum over, let's call them t. Yes? Okay. So this is going to be tij 0, 1. And what's the condition? 0 has to be the product ij of the tij. And here you get basically beta ij to the tij. And here you get bij to the 1 minus tij. Okay. All right. So these are the two products that we're dealing with. Okay. So that's good? Okay. Now, what we want at the end of the day is to say something about the product of alpha and beta. I need to multiply these two because at the end of the day, I want to regroup this guy and this guy. Okay. So I can multiply these guys. All right? And if I multiply these guys, you can now see that there's an S and there's a T. You really need the S and the T. So it's great to have a large board. The problem with the large board is that one is very hesitant to erase. So let me use what we have. So I want to multiply this guy with this guy. And I claim that if you multiply these two expressions, what you end up with is product of alpha ij, beta ij, yes, plus this massive sum over Sij, Tij, and now it has to be the case that the product of Sij, Tij, at least one of them has to be 0. Okay, and then he writes the product of these sums. So this is the sum over basically everything else. But I don't particularly care about this expression, but let me write it just for the sake of sanity. So if I multiply everything else, it's going to look something like alpha ij to the, oh, let's ask for help. Beta alpha ij times what?
Wait, 2 a power or just times?
I think we need the power, right?
To the Sij?
Yeah, so the Sij, absolutely, times beta ij to the Tij. Do we agree? And then we have the rest, which is, what is the rest going to be? It's going to be beta, and so it's going to be now Aij to the 1 minus Sij, and then Bij to the 1 minus Tij. Yes?
What about the cross terms?
I think I've accounted for the cross terms. No?
Yes.
I think by putting this exponent on the Sij and Tij, I've also accounted for the cross terms as well. Because the Sij could be 1, Tij could be 1.
Because the sign of the summation is not the sign of the.
Okay.
Yeah, this is where all the mess in the proof is. There's nothing insightful happening here other than the fact that I've isolated alpha ij and beta ij. All right? Okay, good. Now we're done with algebra. We're now going to do some combinatorics or graph theory. Okay, so what I want to point out at this point in the argument is that this expression here is basically the polynomial for GF. All right?
PF.
Yeah, PF, exactly. Okay, so let's point this out. So is it okay now? Is it okay to erase the top? Are we going to remember what alpha ij and beta ij are? So, okay, I don't have a choice anyway. And we don't have all night, so all day. So the point I want to make is that product of xj minus xi, I different from j, times alpha ij times beta ij, this thing is pf. This is a polynomial. Okay. All right. So what's important to notice is that the polynomial that I've just expressed, this polynomial in pf, it has definitely depends on the variables x0 all the way up to xn minus 1. Do we agree? Okay. But it also has some meta-variable dependence. In other words, there are some expressions when I write down the polynomial, if you think about f as an indeterminate, there are some expressions where I write x of fi, and there are places where I write x f2 of I. Okay? So if you think about this as a formal expression, where f is some undeterminate function, there are places where I write x of I, and there are places where I write x f2 of I. And if I don't tell you what f is, you actually don't know which variable these guys correspond to. That's the sense in which I'm calling them meta variables. This is a variable that's not completely specified until you tell me f. And this is a variable that's not completely specified until you tell me f. Now, this expression as a whole should not depend on these meta variables because they should cancel out. We did a telescoping where we did plus and minus for these guys. So these meta variables that I've introduced in the argument are completely artificial. They should play no role at all in the whole expression. If I set them to 0, nothing should happen. If I set them to 1, nothing should happen. Yes? However, now we're ready to set up our proof by contradiction. Okay? All right. So I emphasize that in the expression as a whole, these meta variables play no role whatsoever because they cancel out. Okay. So now assume for the sake of contradiction, that PF, assume for the sake of contradiction, that PF is congruent to 0 and PF2 is not congruent to 0. So this would violate the statement of the lemma because this is GF2 being graceful and GF being not graceful. Okay, so we assume this. So if you assume that PF is congruent to 0, that means that in my expression, I can totally cross out this guy. I can remove it. All right? So I'm going to call the remaining polynomial, the one where you remove it, I'm going to call it RFF2. I'm going to think about this polynomial now. First observation. This polynomial now depends non-trivially on the bad meta variables. They no longer cancel out. Why? Because some meta variables are here. Explicitly, we see them from PF. Right? They're here, and some of them are here. And they do not cancel out now. Okay. So now, this polynomial depends non-trivially on the meta variables. But maybe that's okay. Maybe when I plug in the values over the lattice, Zn to the Zn, they all vanish. The meta variable vanish. Maybe that doesn't cause any trouble. It turns out that's not true. Because if I go in here, PF, and I set all these guys to 0, PF does not vanish identically. So in the expression of PF, remember the expression of PF, let me write down the expression of PF so we can see. So the expression of PF looks something like this. Product I different from j, xj minus xi. And here you have x f of j minus xj squared minus x f of I minus xi squared. If you set this guy to 0, and you set this guy to 0, then what you're basically looking at is the star, right? This is xf. You basically set you basically turn your function into the star. And this polynomial does not vanish identically on our lattice. Right? This polynomial is basically product of xj minus xi times xj squared minus xi squared. And this polynomial, we know if you plug in 0 for x0 and anything for any other, this polynomial does not vanish. So what this tells us is that this RF, F2, depends non-trivially on the meta variables xfi, even on the lattice Zn to the Zn. This guy depends non-trivially on xfi. This guy depends non-trivially on xfi. And they both depend non-trivially on xfi on our lattice. So even if you plug in values on their lattice, these guys play a role. They play a non-trivial role. This xfi play a non-trivial role. Okay? All right. So what I did is to explain in words the non-trivial dependence on xfi. In the paper, I go in more details. But once you make that observation, you have a home run. Why? Because the equality we have here says the following. It says that pf2, 2 of x, is equal to, is congruent to rf2 of x. This is what we're saying. Now the automorphism group on this side is at gf2. And to prove that the automorphism group of this guy is at gf2, we use the ZB lemma. We said, evaluate this on the lattice. And if you evaluate this on the lattice, the automorphism group is the same as the automorphism group of the undirected graph. Inverse. Minus R. So the automorphism group on the right-hand side is the automorphism group of GF2. However, on the left, on the other side of the equal sign, on this part, the automorphism group cannot be at GF because this expression depends on your XF of I. In particular, I can describe a permutation. I can describe a permutation that cannot be in the automorphism group. So on the right-hand side, this is the patch line. So on the right-hand side, there is, you can assume, and I'll justify this in a second, you can assume that there's an edge, there's a path of length 2, like this. So you have I, f of I, and f2 of I. You can assume that you have a path like this. And if you have a path like this guy stands for xf of I, this guy stands for xi, and this guy stands for xf2 of I. Now, if you look at this part of the graph in the iterate, when you compose the function with itself, what happens, so let me put here the loop edge without the loss of generality, what happens is that you end up with something like this. x2 of I, this does this is I, and this is f of I. So what this says is that you can permute in f2, you can permute xi with xf of I. This permutation in f2 is fine. This permutation in f is not fine. So if your polynomial depends non-trivially on xf of I, you will not be able to permute xi and xf of I. Okay. So, what I have to justify at this point is that you can assume that this happens in the graph. How do you know? How do you know that for a given tree, you can assume this? Is it clear? I know I went a bit fast, but I should give time for questions. Questions? No questions? Where did I lose you guys? Which part of the argument did I lose you guys? Should we start from the beginning?
Can you explain why, we split R, F, F2X part, we can't, it is the automorphism
of this part?
Yes.
Yeah, what is the automorphism of this part? Sure. So remember the expression of RF2 is right here. This is the expression of RF2. Right? RF2. We've assumed, for the sake of contradiction, that the alpha I, beta I was 0. Alpha ij, beta ij, we assumed that was 0. Right? Remember, there was a part that we pulled out. We pulled out alpha ij, and we pulled out beta ij. This was the part we had before. I different from j. And we said that this part is pf. Everything else is R of 2. For the sake of contradiction, we assume that PF was congruent to 0. This whole expression, everything together, we said was PF2. That's where we started. We started from PF2 and we did the telescoping. Okay. Now, if this part is congruent to 0, you can remove it. But if you remove this part, then what you're saying is that the automorphism group of everything here is the same as the automorphism group of PF2. Because when you look at the canonical representative of PF2 and this polynomial should be the same. And the automorphism group of a non-vanishing, we said it doesn't vanish, the automorphism group of a non-vanishing canonical representative is the same as the automorphism group of PF2. So does that answer your question?
Yes.
So the point is that if this part vanishes, it tells me that this RFF2 has automorphism group, basically AutoGF2. This is where we use the lemma, right? Okay. So that, any other question? Any other question? Where did I lose anybody else?
How do we proceed after that step?
After which step? Okay. So here, okay, so are we good with this congruence identity?
Yes.
Okay, all right, good. So now we have this congruence identity. Let's start doing our analysis. So I'm saying that if you give me a tree, I want to compare the automorphism group of GF union GF inverse minus the root. I want to compare this to the automorphism group of GF2 union GF2 inverse, minus the root. The root is the same in both trees. Yes? Okay. So I want to compare these two automorphism groups, and I want to argue that one is bigger than the other. Now, if you give me a tree that is gracefully labeled, give me some tree, let's say this subcomponent of the tree, and you tell me that this tree has a graceful labeling, all right? I can move the loop edge around and reorient the edges, and this new tree that I get is also gracefully labeled. So moving the loop edge does not change the graceful property. So I claim that you can always pick some vertex where you place the loop edge, and these two automorphism groups are going to be different. Okay? Now let me show you how you choose that vertex. So you make two choices. If the tree is like this, it has a leaf path of length 2. That means a leaf of length 2 with an extension like this. Then you place the loop edge here. And if you place the loop edge here, everything else here, I don't really care. If you place the loop edge here, and this is your GF, when you look at GF2, it's going to look something like this. Right? So if you look at, this is GF, this is GF2. Again, I don't care about what's happening here. So in GF2, you can permute these two guys. This guy was xi, this guy was xf of I, and this guy is xf2 of I. Do we agree? Here, this is xf2 of I, this is xi, and this is xf of I. Question?
No, you're fine.
Oh, okay, fine, okay, all right. So when you have this scenario, you have a permutation, which is in UpGF2 that is not here. And crucially, I'm using the fact that, in this graph, this xf of I and xi, this transposition doesn't cause any trouble, but here the transposition causes trouble. So far, so good? Okay, all right. But the person could say, well, what if you don't have a path of length 2? What if every leaf does not have an extension? What do? Well, if your leaf does not have an extension, then your tree necessarily has a cherry. So your tree looks something like this if you have more than 3 vertices. If your tree does not have an extension like this, leaf path of length 2, then it has something like this. Right? You're always preventing me to have a leaf that is 2, then you have to force these guys to go. You could have more edges. This is fine. You can have more edges on the leaf cherry, but there has to be at least 1 leaf cherry. If you have a leaf cherry, then you do this. You place the loop edge on top of the leaf cherry. And if you place the loop edge on top of the left leaf cherry, this is GF, what you get is a tree that looks like this. So let's draw GF2. So what is GF2 going to look like? Any idea?
It has all 3 things.
Exactly, all 3 things now point here. And now you have a permutation, so you can permute these 2. Whereas here you cannot permute these 2. So without loss of generality, because we're free to put the loop edge wherever we want, we can assume that we're either in this scenario or this scenario. So there's always an xi, xf of I that we cannot permute in GF, but we can permute in GF2. Okay, so the bird's eye view is that on the right-hand side of the equality, PF2 here, when you had PF2 on the right-hand side, PF2 tells you that you can permute these vertices, no problem. You can permute these vertices, no problem. The problem is that when you look on the right-hand side, when you have this non-trivial dependence on xf of I, you cannot permute. You cannot permute the 2 edges. So that's where the contradiction is. It's messy to write down the expressions, but at the end of the day, what we want to argue is that there is a permutation here in the automorphism group of this polynomial, which is not in here. There has to be one non-vanishing term that depends on this xf of I. And I know there has to be one because the polynomial depends non-trivially on xf of I, on the lattice. And therefore, I cannot permute. I cannot do on the right-hand side this permutation of the values. I can't permute these 2 guys. Because the right-hand side sees this guy. He sees this guy and he also sees this guy. And you can actually identify the expression on the right-hand side that sees both. You cannot permute these. So if you cannot permute this here, and you can permute these here, you have a contradiction. You cannot have a permutation that is in the automorphism group on the left-hand side, that is not on the automorphism group on the right-hand side. So you get a contradiction. From that contradiction, you conclude that PF2 is P. If PF2 has to be congruent to 0, if PF is congruent to 0. But I took some shortcuts when I was presenting on the board. That's why I ran into trouble. If I follow the paper's argument, it's much easier to actually see where that term is. You want to be able to identify among these guys, where is the term that depends on xf of I? And you want to show that that term cannot vanish. There has to be a term that does not vanish, that contains xf of I. And that term is not invariant to that permutation. And you cannot map it to any other term. So that gives you the contradiction. So here, there's a specific permutation that we're after. We're after this permutation. Exchanging xi and xf of I. And here, you can permute them fine. No problem. But here you can't. And here, you can permute them fine, but here you cannot. And that's basically the idea for the contradiction. Okay, so now you guys know the whole proof of the composition lemma. That's basically the whole proof argument. All right, so director, we're done. All right? Okay.